This is a video series of the topic of statistical estimation. We have learned some basic concepts about estimation methods like linear least squares, prediction error method. And in this direction, in this video series, we're going to switch to statistical approach. So this is an approach where we also take into account some random entities in the model. Okay, like when your model structure has noise, now we assume that, all right, we have some information about the noise. We just say we don't just say that, oh, noise is unknown and there is nothing we can do about it. In this approach, we assume that probably you know some moments of noise, you know some variance, you know some statistical distribution, you know it's the PDF and everything. So try to use that statistical information about the noise incorporated in your estimation process. So this approach has three fundamental estimation methods. These are mean square error estimation, or MMSE, maximum likelihood estimation, MLE, maximum a posteriori estimation. And then we're gonna also present some important inequality about estimator. This is called Kramer-Rao bound. It is just basically say something about the covariance of your theta hat. There's going to be a lower bound on that. And at the end, we will present some statistical properties of MLE. Okay, that the MLE estimate, maximum likelihood estimator, is consistent and has a limiting normal distribution. So these are all topics in this chapter, and in this video clip, I think we will focus on the first method, the MMSE, the minimum mean square error estimation. So the fundamental concept of MMSE require the concept of conditional expectation. In this scenario, you have variable x and y as random variables, and these two guys are jointly distributed with the joint distribution. In this lecture, you will see that probably I abuse my notation a little bit. I always use a lowercase letter, but I also refer it to the random variable. I also use this as a dummy variable in a function. So I hope that so whenever y and x are dummy variable, it basically means it's a dummy variable. But I also use it just to present x and y as if they are random variable as well, which is not technically correct in terms of mathematical notation. It should be like big X given big Y instead. But just to make my goal is just to make this notation clear. So I would like to state that first. Okay. So X and Y are jointly distributed. It means that whatever happened with Y also has an effect on X. The values of Y at a particular outcome, like when Y equals 1, that's going to affect on the occurrence of X. Okay, that's the meaning of being jointly distributed. So we are interested in finding a mean of X when the value of Y is given. That's conditional expectation. And mathematically, everyone knows that, okay, find the mean of X, right? But with respect to conditional distribution. So the PDF here is a conditional PDF of X given Y. That's the definition. We know that the conditional density is given by the joint distribution normalized by the marginal of Y. Okay, this is clear. You say, why are we interested in this quantity? Because you might say, okay, if you know nothing about if you don't have y at all, okay, you know that these two guys are related, but you have no information about y. What is a common way, or maybe what is the first thing you think of when I ask you, okay, how can you estimate x? X is a random variable, right? Some might say, okay, probably use the mean, right? The mean is a very first, and is a very first thing you think of a random variable. It's just a very approximate way to talk about a random variable, like use the first moment. But the thing is, now you have more information. You have more information. You know that these two guys are related. And then if I give a value of y to you, that should help you to estimate x better. And then you say, okay, I use the conditional mean because that's that is to say that you still use the first moment to describe x roughly. Okay. Now we're gonna see that that information, that conditional mean, is actually the best way to describe x when y is given. And we're gonna see next what is best, what is the quantitative way of saying that that is the best. Now I would like to state some facts about conditional mean first. First of all, the conditional mean of y, x given y, is a function of y. All right. I hope that is clear, because I mean, when y is given, like y is given to 1, you find like when you find the mean of x, it means that you aggregate all the value of possible x, right? By this operation, you integrate all the values of x. So when y equals 1, e of x, let's say e of x of conditioning on y given 1 is, suppose it's 2, right? E of x y given as 2, probably the mean is 3, right? So it means that the values of the mean here depends on the given values of y. So conceptually, we just simply say that conditional mean of x given y is a function of y. All right. The second bullet, the second important result, is called the law of iterated expectation. This guy is a function of y, right? Conditional mean of x given y. If you take the expectation again with respect to y, surprisingly, it is equal to expectation of x. Okay, this can be shown quickly. All right, so I'm going to show the left-hand side, right? So e of x given y by the definition is this, right? All right, this is supposed to be a function of y. All right, so I'm going to find the expectation again. So what's the next step? So if I find the expectation of this again, I should integrate it, right? I should integrate it with respect to which distribution? City Park.
Y.
Right? So I should multiply it with
dy. Well, fy.
Fy, right? Fy, and then integrate it with respect to y. Okay. But then, okay, what's the connection between conditional density and the joint and everything? I just plug it there. So the conditional density is gonna be the joint, right, divided by the marginal, right? Okay, and then these marginal of y are cancelled out. All right. And then if I can swap the order of integration, I will integrate with respect to y first. So what do I get after I integrate it with respect to y? Total. Top. I integrate the joint distribution with respect to y, with respect to one variable. Totok is not here, sorry. Yeah, I ping.
Maybe we got a function of it.
Yes, we get the marginal of x, right? We integrate the joint with respect to y, we get the marginal of x. Oh, sorry, this is dx. And that is what? That is integrate x, marginal of x, that is ex. All right. So this is important. This is called a law of iterated expectation. Okay. And then we can we're gonna use these results in the next couple of slides. And then this result can be also extended in the third bullet. If you have any scalar function gy where the mean of gy is finite, okay, we can show that. Okay, take a look at the first term. This is the x subtracted by the conditional mean. Okay, if you multiply this guy with gy with any function of y under this condition as well, this expectation is 0. The meaning, the interpretation of this equation is the following. Like, think about y as a measurement, think about y as the data, observations, all right? You think the conditional mean of x given y is the best way of estimating x in the situation that y is given. When you subtract this conditional mean from x, this is like a residual, right? A residual error when you try to use this as an x hat. Okay? When you try to use data or observations of y in order to predict x. And that is the residual error. So residual error times dy, this is a way to interpret the formula. It just says that when you have two terms, like the expectation of 0, you can say that, oh, the residual error now is uncorrelated with gy. This residual error is nice, is optimal in the sense that it's always uncorrelated with any functions of data, any function of observations. Okay, mathematically this can be shown, this can be verified. I mean, please do it yourself, like use the same trick as we use in the second bullet. Okay, but we're gonna rely on this result when we talk about MMSE, which we are about to see. So here I present the method. This is very fundamental. This is mean square estimation. Again, this is the scenario where we have two random variable x and y. It has they have the joint distribution. The problem setting is very simple. X and y, you only have measurements of y, but you don't have x. All right. Your goal is you would like to estimate x. You know these guys are related and y is measurable. So you're going to propose a scheme. You're going to propose as an estimator that, okay, probably I'm going to use the information of my measurements y, but I'm going to propose some mapping h, a function that gives me x hat. Okay, but now I'm going to put an objective that, okay, my estimator should be optimal in some sense, and that sense is a sense where my x hat should minimizes the mean square error. All right, so mean square error, first I measure the error, I subtract my x hat from x, right, from the true value, but the true value is not known. Okay, my x could be a vector, so that's why the next step is I use the norm. I use the norm and norm square to measure the size of the error. Okay, but the thing is, this quantity at this point is also, you know, both x and y are random variables, so these quantities are random. So that's why I put the next step is I put the expectation. So that it means that this is the ensemble average of the mean square, sorry, ensemble average of the error squared. All right. So mathematically, so we just say, okay, we choose y, we choose h, we choose a function of h that minimize this guy. The results, we're gonna show that, oh, hy, the one that minimizes the mean square error, is simply the conditional mean. And to prove it, it's very simple as well. Let's see in the next step, right? So first, I would like to mention, remember that when I introduced the conditional mean of x given y, because we think that, okay, probably that's the quickest way to estimate x when y is given, but it turns out that, oh, the conditional mean is also optimal, is the best one. It's the best one, and is the best in the sense of minimizing MMSE. All right. Okay, to show the optimality of the conditional mean, okay, we're going to use the result, the previous result, that the residual error in estimating x when you use the conditional mean, okay, we use this result, that the residual error is uncorrelated with any function of y. Okay, now, basically, first, we just expand the square. Okay, sorry, not expanding the square yet. Consider the term inside here, x minus hy, right? So I'm going to add and subtract the conditional mean. All right, I add and subtract. That doesn't change the quantity in the yellow circle. And then, because I know that the reason why I do this because of the following. When you have the norm square of two terms, Napat, can you expand this norm square? Napat is not here. Sitipak.
Norm of u square
Mm-hmm.
plus 2 plus 2u transpose v and plus norm v square.
Okay, all right. You see that like when you expand the sum of the norm of the sum, you're going to have the crossing term, right? The inner product of the crossing term. And then, so suppose u and v are a random variable, you're going to have that, like, if you take expectation, so it's going to be expectation of, you know, of all the terms. Now, I would like to take I would like to split, right? The reason why I add and subtract conditional mean of x given y, so that I can see these term in two parentheses, in two groups, all right? So considering that when you expand the norm square, now the first term is this, all right? And the norm square of the second term is this. But we also have the crossing term, right? So the crossing term is going to be x minus e x given y, right? And then you're going to have what? You're going to have e of x given y minus, minus hy, right? Everyone follow this? The term I wrote it here is a crossing term, right? The crossing term. Okay, now let's take a look at the term on the right hand side. The right hand side, e of x given y, as I mentioned, this is a function of y, right? So h of y is also obviously a function of y. So we conclude that the pink term is a function of y, right? But based on the previous result, what did we have? We had that when you have the residual error of x, when you use the conditional mean of x given y, this residual error is always uncorrelated with any function of y, which means, what is this term, Ping? This residual error, right?
Residual error of y.
Yeah. So residual error, and you try to kind of find the expectation with the ping term, but the ping term is function of y. So after the expectation, it is ping.
Yes, it becomes 0.
It becomes 0. All right. So when it becomes 0, that's why you have you only have the what the expectation of the norm square. All right. The blue and the yellow one. Now, take a look on the left hand side. The left hand side says this is the mean square error of what? Of using any function of y. All right. Look at the blue term. All right. The blue term is not a function of h. It's nothing to do with the h, right? Now you like, this is kind of optimization. Like you have a free choice on h, right? So what you can do, you can only twist or choose or do something about it with the yellow term, because this is a term you can like vary the choice of h. But the thing is, the left hand side is the sum of two terms that are always non-negative, right? Expectation of something square is always non-negative. So in order to minimize the left hand side, now we take a look at the yellow term, right? So why do we choose to something else? But the only way that makes the yellow term minimum is to make it 0, right? And that should be obtained by choosing the conditional mean of x given y. All right? Is it clear? Like the yellow term is non-negative. Everyone agree? Right?
Yes, yes.
So we should make this guy 0, because that's possible. And to achieve it, of course, you pick h of y as conditional mean of x given y. All right, that is important conclusion. This is the result that when x and y are jointly distributed, the best way, when y is measurable, the best way of estimating x is to use conditional mean. It cannot be nothing else. Okay. Now, I would like to give some examples, easy examples as well. The Gaussian case, let me mention this, which mean from the definition of the conditional mean, the conditional mean of x given y is x, and this, right? Which mean in order to find the best estimator of x, you need to know the conditional density. And to know the conditional density, you must know the distribution. You must know the joint distribution, right? You must know the joint distribution between x and y. But now we would like to give you some example when the joint distribution is Gaussian. Okay, just one particular case. We know that when x and y are jointly Gaussian, we can say that the covariant matrix are partitioned in this way. All right, the mean is partitioned in this way. And we also have the results that when you have x and y as a vector, if you want to find the conditional variable, the variable x given y is also a Gaussian variable, right? And this is what we learned from Gaussian vector. X of x given y is also Gaussian, and the conditional density is given by Gaussian, where the conditional mean is this expression, conditional covariant is this. This is the true complement of Ex of sigma xx in the block of sigma. We have seen this before, right, when we learned Gaussian vector. So that's why the result is very simple. When x and y are jointly Gaussian, the best way of estimating x when y is given is the conditional mean. And when we take a look at the conditional mean expression, what we see is that this is linear function in y. Okay, and in order to compute this value, you must know what? You must know the cross covariance between x and y and the covariance of y. Okay, for example, when y is 2, right? When y is 2, so the term that I circle with the blue term, which means this term must be known in order to compute the conditional mean. All right. When y equals to 2, then you just plug it in. Y equals to 2. Okay. Now, so basically, the known values of y will be adjusted as a deviation from its mean, right? And it will be amplified, or it can be maybe suppressed or amplified. It depends on this value, right? So if the cross covariance is big, so what's the meaning? City Park?
Mean the conditional mean is larger.
It means that, okay, like think about like conditional mean. Obviously conditional mean is not the same thing as the mean of x, right? This is not the same thing. Okay. When the cross covariance of x and y are big, which means these two guys tend to have the same tendency. When y is big, it is unlikely that x is also big, right? So, which means when y is given, and if cross covariance of x and y is big, which means the effect of that known values of y should have a very big influence in order to adjust the mean of x, right? Because this portion will be the portion you add up with the mean of x. If y is not known, of course you're going to use the mean in order to estimate x, right? But now x is known, the effect of the known values of y, right, will be big or small, depend on this gain. And that gain, the cross covariance of x and y, just give you that proportional scaling. For Gaussian case, let me conclude again that the result conditional mean is linear in y. And when everything is linear, this is simple, right? Computation is very simple and everything. To conclude, probably we can just end up the clip here. Conditional mean of x given y is the best way to estimate x. When y is given, is best in the sense of it gives you the minimum mean square error. Typically, the conditional mean of x given y is nonlinear in y, right? And it depends on the joint distribution between x and y. If you consider the Gaussian case, that MMSE estimator happens to be linear, right? It's linear, and the residual error after the estimation satisfy the orthogonal principle. Residual, oh sorry, I missed the expectation here. Expectation between residual error with any functions of the measurements is always 0. Residual error is always uncorrelated with any function of y. Okay. In the next couple slides, which is probably next lecture, the MMSE can be difficult to evaluate because you must know the joint distribution and calculate, right, the integral and everything. One can restrict to use a particular choice, all right, a linear class, a linear form of MMSE.